Again, our levels of organization, populations, communities, ecosystems, landscapes. If you want to put another one there, biomes, we'll talk about those a little bit. Ultimately, all the way up to the whole biosphere. So again, I already talked about what populations are, communities, multiple species, ecosystems, bringing in the abiotic part. Landscape would be multiple ecosystems in a given area. In the biosphere, that's all life on Earth. So all the way from the bacteria down in the deepest cracks in the ground to the, again, bacteria, kind of at the extremes, and spores and things like that blowing in the wind up in the sky. So all the way, the whole area on Earth where you have living things is the biosphere. And these different levels of organization will have their own distinctive features. Any one individual is a part of a population. If we have a population, there are often changes in that population. And these changes are the population dynamics, what's going on with it. In particular, a common thing to be looking at is a population. Is it staying the same? Or is it growing? Are we getting more individuals in our population? Or is it shrinking? A decline in our population? Lots of things are going to affect this. How successful are the members of the population at reproducing? If they have lots of young, if they have very few. Evolution, again, change in gene frequency in population. So yeah, that's population level changes. And those genes may impact how the organisms are able to live, how well they do in different situations. More generally, genetics, what genes they have and don't have. And of course, populations make up parts of communities and ecosystems. So what's going on with other populations and the physical environment are going to affect our populations as well. So we can look at all sorts of numbers here. Population density, that's how many individuals there are in a given area. For example, we could count how many people live in the city or town limits for Boiling Springs. That's the population density for humans within Boiling Springs. It's going to be somewhat different from the population density, say, in downtown New York City or in northern Alaska. We have variation there. Population dispersion, how spread out or concentrated a population is. For example, Boiling Springs, okay, we've got so many people, I think it's on the order of 4,000 some within the town limits. But let's say we've got a big event, say maybe graduation, and now all of a sudden a lot of that population is all concentrated within Boiling Springs, right around, well, in the future our graduations will be in the stadium. So we'll have the population much more concentrated in one spot. Then after graduation's over, people are starting to head out and maybe go to a restaurant, go home to pick stuff up, whatnot. All of a sudden, now they're more spread out. So different dispersions there. Birth and death rates. No surprise, that has a lot to do with how many individuals you got, how many are born, how many die. Putting those together will lead to growth rates. Now, of course, there's one more thing besides being born and die. At least for animals, individuals could move. Boiling Springs could get more people, not just by there being lots of babies here, but by lots of already existing people moving in from somewhere else. Conversely, if lots of people move away, the population would drop even though we don't have lots of folks dying. So some more things there. Survivorship. How likely is it for one individual to be still alive at some point in the future, say the next year, or whatever is convenient for a particular analysis? All these will relate to the age structure. Do we have lots of young individuals, and this is a species that just kind of cranks out lots and lots of seeds or eggs or whatever, and hopes a few of them make it? Then you've got lots and lots of young ones and not very many older ones. Or you can have a more even pattern of similar numbers through the age structure, or maybe you've got more old and fewer young. Different patterns there. Again, evolution, this can be due to natural selection, where there are factors that favor some allele versus another. But also there's random variation. Say, for example, if we decide we're going to found a colony out in space somewhere, we've gotten a bunch of people loaded into a spaceship and they get there. Okay, that group of people will have a certain number of folks who, say, have black hair. Let's use hair color as an example. Okay, now what color your hair is doesn't generally make a whole lot of difference. It affects how you look, but doesn't affect how you survive, that sort of thing. But let's say for some just chance, with that first generation of settlers for our new space colony, all the redheads happen to have a dozen kids each, and folks with brown or black or blonde hair don't have as many. Well, next generation, we're going to see more redheads proportionally than we had before, just as a kind of random variation. That's the sort of thing that's talking about. Again, population density. How many individuals of our species are there in a particular area, or volume if it's something that may be up in the air or spread around the water. A given environment can support only so many individuals, so there will be a limit to the maximum population density in a given setting. Why? Well, there are both biological and abiotic factors that may play a role. Usually both of them are going on in any one situation. Population dispersion. How close together or spread out do the individuals in a population tend to be? So, for example, organisms could just be randomly scattered. Turns out that's not very commonly true, but it could occur under certain situations. And so that's what a random distribution looks like. When people try to draw a random distribution, they actually tend to draw things more spread out than is truly random. Often, instead of random, things are clumped. For example, here's a school of fish. Here is not a school of fish out there. The number of fish, they're concentrated into one patch, not as spread out. Like the diagram here, things are obviously clumped in there. This can happen for several reasons. One is if resources tend to be concentrated. For example, trying to maintain social distancing at the store, but there's a crowd at the toilet paper. Resources are concentrated in one spot, and everybody's trying to get them. So that would lead to a clumped pattern. Or, in the case of schooling fish, for example, having more eyes to watch out for predators, and lots of individuals together makes it somewhat trickier for the predator to say, I'm going to get that one. Wait, was it that one or that one? Which way do I go to chase it? It's more challenging to keep track of individuals with a school than just one by itself. So there are a couple of ways where this clumping behavior might be helpful against predators. Or, obviously not so much the case of fish, but certainly could be for some of the things living down on the bottom if they don't have a great way to spread around. For example, a plant where the seeds don't travel all that far, well, then the baby plants are going to tend to be close to the adult. No surprise there. And this will be true for certain types of animals. Now, most corals, though of course the adult corals there and isn't going anywhere, they can release eggs and sperm that fertilize out in the water and drift around the plankton. So those can spread around quite a bit. But there are other things which lay eggs that stay on the bottom, or maybe even don't lay eggs, directly give birth to young that stay on the bottom. Those, of course, can quite easily be more clumped. On the other hand, we have cases where things are somewhat more spread out than random. For example, these gannets. These happen to be Cape gannets from South Africa, but they are very, very similar to the ones that we get off our coast in winter. And these birds, they'll have their nest, and this is my nest. I can reach this far and peck you if you get too close while I'm sitting on my nest. So the birds are spread out to the extent that they can be on this area as a more dispersed, more spread out, uniform dispersion type of pattern. So this happens if they're moving out to avoid competition, like in this case for the nesting space, trying to spread out as much as they can. And individuals tend to repel close neighbors. This can be obviously fairly easy for the bird. It's got a beak you can peck with, but plants can even do this by creating chemicals that tend to discourage things from growing too close. Or perhaps a tree makes enough shade that seeds won't grow underneath it. They have to be further out. Territorial patterns in the birds here. Now, as a complication, each of these gannets is spread out about equally. And then you got the ones in the air. No gannet is building its nest on the ocean. This does not work. So this whole colony is a clump. But within the colony, they are dispersed. One complication of this and many other things, it does depend on what scale you're looking at.